Hello and Assalamu alaikum. My name is Mohammed Sabil Hassan and I will be giving a short summary and feedback regarding the CS351 Artificial Intelligence course offered at the Habib University. I'm going to start off where we started off in our course at Habib. So I'm just going to quote Professor John McCarthy. He is considered the father of artificial intelligence, a former professor at Stanford. So, as he said, intelligence is the computational part of the ability to achieve goals in the world. And I'm going to also quote him on the question when someone asked him what is artificial intelligence. Um, According to him, it is science and engineering of making intelligent machines, especially intelligent computer programs. When discussing the milestones of artificial intelligence, usually these questions pop up. Does AI aim to put human mind into the computer? Does AI aim at human level intelligence? Well, in order to explain them, I will sort of like elaborate on intelligence. Something is defined intelligent when it can learn, solve a particular problem with correct reasoning, or make correct decisions. So all of these characteristics are found in humans, hence we label humans as intelligent. So the main goal of artificial intelligence is to make these machines intelligent by making them function just like a human brain does. Well, after a brief introduction into the course, we tackled on some common problems. One of the commons present on the screen is the problem that we looked into, the 8-puzzle problem. It's a problem where there is a 3 by 3 grid with 8 of the squares labeled 1 to 8, and there's a 1 empty square. So what we have to do in this problem that um, we are given any current state and we have to achieve the goal state as shown on the screen. So how we tackled the problem was that we defined the search space. The search space included the initial state as well as the goal state and the other intermediate state. Then we chose, a search algorithm. And now the first search algorithms that we learned or revised, I would say, were the uninformed or the blind searches, known as the breadth first search or the depth first search algorithms. Although we looked into many examples of solving problems using DFS and BFS, one that I found pretty interesting was the missionaries and cannibals example, because I've played this game as a child and I was curious as a child what the underlying mechanism behind the whole game was. So this was a pretty interesting approach in my opinion. The bridge crossing problem was also a problem that I found really interesting as I invested quite a bit of my time solving this as correctly as possible. Applying DFS on this problem, I searched for the solution by following the successor until I reached the leaf node. If I had used BFS, I would have made an exhaustive search by searching an entire level before going down another level. In this case, DFS proved to be efficient as my goal nodes were present in the first leaf node, and saving a lot of my time searching at each level. Further on, we also learned about uninformed searches, also known as heuristic searches. So, and we particularly looked into the algorithms of two searches. One is the greedy best first search, and the second one is the A star algorithm. And while they are called informed searches, it is due to the fact that they use additional information about nodes that have not yet been explored to decide which nodes to examine next. A popular example that we looked into was the Romania one. In order to solve a problem using best first search. So in this example, different cities with their distances recording from a specific city has been written in the diagram. And using a heuristic evaluation function, the best first search was able to figure out its next step or the next node that it was about to go to in order to solve the problem. Since the heuristic function in this case, it determines the straight line distance from the goal node. So what the best first algorithm did in this case was it selected its node that has the shortest distance among the other successor. And it followed this particular mechanism of following the particular successor with the shortest direct distance towards the goal node. What must be noted here is that this would never ensure that an optimal path and an optimal solution um, would be a result of a best first search. In contrast to a greedy best first search algorithm, we learned about the A-star algorithm and used it in our assignment one. The A-star algorithm always ensures that an optimal path is reached. Here in the picture, you can also see that it's an informed search since another comma separated file is provided known as heuristic other than the files named as connection. So what the A-star algorithm actually does is its evaluation function is comprises of two values. The one value is the step cost and the other value is the heuristic function that we have defined. The step cost will be the particular cost of going down to a particular successor or going down a particular step. It can be a distance or a cost or any value that we have assigned. Whereas the heuristic value from that successor will be the total distance or the total cost from that current successor to the goal node. What the A star does, it is calculates the sum of the step cost and the heuristic value at each successor, and then compares that function value with other successors or the other neighboring nodes from the current node. Then it goes down the path or follows the path whose function value is the lowest, ensuring the most optimal path from the initial state to the goal state. In other problems that we encountered in the course, we were concerned about the optimal value, but not about the optimal path that will lead to that value. So this means that the goal state is important, but the path that leads to the goal state is not that important. So this is the whole mechanism behind optimization. And the two algorithms that we learned by far for optimizing a certain function or optimizing a certain problem, one is the hill climbing and the other is the simulated annealing. So in hill climbing, we can start wherever on the function that we want and always choose the best neighbor. The best neighbor is defined as a neighbor which has a function value higher than the current value. And if there are any no such neighbors around the current value, so then just quit and give the current value as the most optimal value. So there are certain problems with it, as there's concepts such as local maxima, and it allows the algorithm to get stuck into local maxima when hill climbing algorithms apply. However, the simulating and annealing technique prevents this from happening by going downhill in order to recover from a local maxima. It performs random search based on the probability of finding an optimized solution if we go downhill. It uses temperature values at first, which give high probability that allows the algorithm to move downhill and escape a local maxima. The value of this temperature obviously goes down gradually. An interesting example we saw was in the assignment. Different functions were provided to us and we have to solve them using simulated annealing, and I've found the visualization part quite fascinating when I saw how the variables change as the function tried to reach its maxima or its minimum. Last but not the least, I would like to briefly discuss the inclusion of AI in two-player games. These two-player games can be efficiently represented using trees called game trees. A game tree is an instance of a tree in which a root node actually represents the state before any moves have been made, and the nodes in the tree represent the possible states of the game, and the arc in the tree represents the player moves. So far, we have learned two algorithms it's written on the screen, the min-max algorithm and the alpha-beta pruning algorithm, in order to solve those problems in the two-player games. A particular example of a min-max algorithm has been displayed on the screen. Um, how this algorithm actually works is based on the characteristic of its predecessor. Its predecessor is minimum, then it selects the minimum values out of its two leaf nodes. If the predecessor has a maximum characteristic, then it chooses a maximum value out of its two successor values. All of these values ultimately lead to the best value towards the root node, which determines the best possible move for one of the players. Although min-max is a very simple algorithm, but it's unsuitable for use in many games such as chess, where the game tree is extremely large. For that cases, we use alpha-beta pruning. As you can see in the picture, that a certain number of nodes have not been visited yet. The one of the players has achieved its best move. This is possible because the alpha-beta pruning algorithm isn't as exhaustive as the min-max algorithm. It uses two values at each predecessor, that's the alpha value and the beta value, and based on the nature of the predecessor, the alpha or beta values are updated, and if the alpha value is greater than or equal to the beta value, there's no need to look into any more successors, and that's why many of the leaf nodes or the other successors go unexplored, yet the algorithm has given the best possible move to one of the players.